Chapter 5 is about gravity. In this chapter, you'll consider the force of gravity, what Galileo thought about motion and gravity, what Newton thought about motion and gravity, how does gravity explain orbital motion, how does gravity explain tides, and what were Einstein's insights about gravity and motion. Space stations and astronauts, as well as planets, moons, stars, and galaxies, follow paths called orbits that are described by three simple laws of motion and a theory of gravity, first understood by Sir Isaac Newton. Sir Isaac Newton added physics interpretations to the mathematical descriptions of astronomy by Copernicus, Galileo, and Kepler. He invented calculus, discovered the three laws of motion, and he also discovered the universal law of mutual gravitation. Galileo found that a falling object is accelerated downward each second. Its velocity increases by 9.8 meters per second, or 32 feet per second. Galileo's observations were that the acceleration of gravity is independent of the mass of the falling object. Newton's first law of motion is that a body continues at rest or in uniform motion in a straight line unless acted upon by some net force. Newton's second law of motion is that the acceleration of a body is inversely proportional to its mass, directly proportional to the net force, and in the same direction as the net force. Newton's third law of motion is that for every action, there's an equal and opposite reaction. Cause and effect. Ancient philosophers argued that objects move because of their tendencies. Newton's second law of motion, force equals mass times acceleration, was the first clear statement of the principle of cause and effect. That is, effect A must be the result of a cause F, or effect acceleration must be the result of a cause force. Without cause and effect, we would never expect to understand how nature works. The law of mutual gravitation is an inverse square law. Any two bodies are attracted to each other through gravitation with a force F proportional to the product of their masses, big M, little m, and inversely proportional to the square of their distance. To understand orbital motions, the universal mutual gravitation law allows us to understand that the orbital motion of planets and moons are that the Earth and the Moon attract each other through gravitation. Earth is much more massive than the Moon. Thus, Earth's gravitational force constantly accelerates the Moon towards the Earth. This acceleration is constantly changing the Moon's direction of motion, holding it on its almost circular orbit. In order to stay on a closed orbit, an object has to be within a certain range of velocities. A satellite above Earth's atmosphere feels no friction and will fall around Earth indefinitely. Earth satellites eventually fall back to Earth if they orbit too low and experience friction with the upper atmosphere. Geosynchronous orbits can orbit the Earth at a distance of about 26,240 miles from Earth's center. A satellite orbits with a period of 24 hours. The satellite orbits eastward, and Earth rotates eastward under the moving satellite. This satellite remains fixed above a spot on the Earth's equator. An object's circular velocity is the lateral velocity it must have to remain in a circular orbit. If the mass of the spaceship is much less than the mass of the Earth, then the circular velocity is velocity equals the square root of the gravitational constant times big M for mass divided by radius. A common misconception is that there is no gravity in space, but space is filled with gravitational forces from objects in the universe, the sun, or the Earth. Just above Earth's atmosphere, the orbital motion of a satellite is almost completely due to Earth's gravity. A weightless astronaut in space is actually falling along a path due to combined gravitational fields. Newton's version of Kepler's third law is that balancing the force called centripetal force necessary to keep an object in circular motion with the gravitational force, an expression equivalent to Kepler's third law is period squared equals semi-axis cubed, where you have the period in years and the semi-major axis in astronomical units. Tides are produced by small differences in the gravitational force exerted on different objects. The side of the Earth nearest the Moon is subject to a larger force than the Earth's center, and that is subject to a larger force than the side farthest from the Moon. Relative to Earth's center, small forces are left over, and that's what causes tides. The lunar gravity acting on the Earth and its oceans are that the Moon's gravity pulls more on the near side of the Earth than on the far side. The subtracting the force on the Earth's center reveals the small outward forces that produce tidal bulges. This interaction is what causes spring tides and neap tides. The sun is also producing tidal effects about half as strong as the moon. Near full and new moon, those two effects add up to cause the spring tides. Near first and third quarter, the two effects work at a right angle, causing the neap tides. Earth's tidal bulges are slightly tilted in the direction of Earth's rotation. Gravitational force pulls the moon slightly forward along its orbit. Newton published Principia in 1687, and that changed astronomy, science, and it also changed the way people think about math and nature. It clearly demonstrated the power of mathematics as a language of precision for the study of nature. And it also showed that the rules that govern the universe are simple. Sir Isaac Newton used the scientific method to discover many things. Part of the scientific method is a hypothesis. A hypothesis can explain past events, or it can predict what will be found if we explore further. If a prediction of a hypothesis is confirmed, scientists gain confidence that the hypothesis is correct. Prediction can point the way to unexplored avenues of knowledge. For example, the Standard Model regarding atomic particles and the forces between them confirmed previous observations. Einstein discovered that Newton's laws of motion were only correct in the lower limits of the speed of light velocities, and this led to his theory of special relativity. This also revised the understanding of gravity and led to Einstein's theory of general relativity. The first postulate of relativity is that the laws of physics are the same for all observers, no matter what their motion, as long as they are not accelerated. The speed of light in a vacuum is constant and will have the same value for all observers, independent of their motion relative to the light source. The first two postulates of the theory of special relativity are: observed mass of a moving particle depends on its velocity. The energy of a body at rest does not equal zero. Instead, we find that E equals rest mass times the speed of light squared. The observed mass of moving electrons depends on their velocity. As the ratio of their velocity to the velocity of light, v over c, v divided by c, increases, the mass of the electrons relative to their mass at rest, m divided by m sub 0, increases. Such relativistic effects are quite evident in particle accelerators, which accelerate atomic particles to very high velocities. The third postulate of relativity is the equivalence principle, and it's a new description of gravity. Observers cannot distinguish locally between inertial forces due to acceleration and uniform gravitational forces due to the presence of a massive body. An observer in a closed spaceship on the surface of a planet feels gravity. In this picture, with the rocket on the launch pad, and this picture beside it, it shows in space with the rocket smoothly firing and accelerating, the spaceship and the observer feels inertial forces that are equivalent to gravitational forces. Mercury's orbit precesses about 42.98 degrees and about 0.04 arc seconds per century faster than predicted by Newton's laws. Even when you ignore the influences of the other planets, Mercury's orbit is not a perfect ellipse. Curved space and time near the Sun distorts the orbit from an ellipse into a rosette to geometrical shapes. The advance of Mercury's perihelion is exaggerated by a factor of about 1 million in this figure, where you see the orbit of Mercury around the Sun. Like a depression in space-time, the curved space-time near the Sun deflects light from the distant stars and makes them to appear to lie slightly farther from the Sun than their true positions. So here's some discussion questions. When a person says he gained weight, does he mean that he gained in mass, gravity, or both mass and gravity? Hint: force equals mass times acceleration, where force is the weight And acceleration is acceleration due to gravity. People who lived before Newton may not have believed in cause and effect as strongly as you do. How do you suppose that affected how they saw their daily lives?